Hello everyone. In this lesson, we will explore related rates. The related rate problems that we are going to work with in this lesson will involve electronic applications. Before we get started with the example, I would like to give the definition for related rates. So, in an equation containing two or more variables, the rate at which one variable changes will affect the rate of change of the remaining variables. Problems involving variables whose rate of change are related is called related rate problems. In solving for related rate problem, the following steps should be taken. I identify some steps here for everyone, and some steps you may not have to follow, and some steps we may have to make sure that we done it correctly. So I put here that determine the equation if it's not given, but most of the time I believe the equation will be given to us, and we identify the variables and the rate. This is the most challenging part of the word problems. We identify the variables and the rates, and then we differentiate both sides of the equation with respect to time. It means that you have to differentiate implicitly, and then we substitute all the given rates and the given values into the equation, and you know that we have to substitute the correct rates and the correct values, and then we solve for the unknown. Alright, so I will go over the step right here. Identify the variables and the rates. So I would like to ask you this question. What is the rate? How do we identify the rate? So to identify the rate, we have to measure it in terms of time. Right? So if you have any variable or any number given to you and its unit is measured per time, then you know that you are given a rate. Okay, so and in previous lesson, we are talking about the rate of change of current, of charge, of voltage. So, and when we talk about the rate, we always talk about the differentiation of that variable with respect to time. So if a unit is given to you in terms of time, so a variable with a unit with respect to time, then you know that it is the rate. So hopefully this will provide us with the correct approach to identify the components that given to us in the word problems regarding related rates. Okay, so before we get started, I would like to remind everyone that we are going to use negative for decreasing and positive for increasing involving the related rate components. Okay, so the answer will work out to be the same. The result will show increasing or decreasing by negative or positive result. So keep this in mind. This is actually quite important. And we make sure that we are using positive and negative, and sometimes it's affected our calculation as well, because if we have a subtraction in differentiating, then the negative and the positive will affect our answer. Alright, so let me give you an example about a related rate problems. So in real life, we experience that all the time, but sometimes we tend to ignore because it seems to be so normal for us. One thing is actually very simple, and we tend not to pay attention to it, is the light bulb. So if I turn on the light for a few seconds, it will just I notice the light, and if you feel the lamp, you just the temperature is just normal. But after 2 or 3 hours, or maybe I left it overnight, and I go near the light and I feel the lamp, and I see that is involving the heat. Okay, so it's hot. So that means that the time affected the heat. So the one variable changes, affecting the other variable. So if the time is just a few seconds, then the heat doesn't affect the heat at all. But then if the time increases, it affects certain components inside that lamp and to make the lamp heating up. Alright, so that's one of the practical problems that we tend to ignore every day. It's happened to your laptop as well. So after a few hours, you may want to let the laptop cool down, or they have the components, they have the fans in order to cool the laptop down, right? So one change it affect the other variables. So in example number 1, I have a very practical example right here by telling you that the electric resistance measured in ohms of a resistor can be affected by time, by the temperature. Okay, so first of all, as I mentioned here, right? Step number 1, determine the equation if it's not given to us, but in this case, it's given to us. So the electric resistance of a resistor is given as R equal to A plus 0.002 times the capital T. In this case is the temperature. So the temperature square times 0.02 plus A would be equal to this electric resistance. So the temperature is measured in degrees Celsius. If the temperature is increasing at the rate of, you see it's identified right here is the rate. So definitely this is the rate. But how do we write this in a mathematical symbol? Okay, so remember in previous lesson we are talking about the rate. That means we are talking about differentiation, right? Differentiate the temperature in terms of time. And then it asks me how fast is the resistance changing when the temperature reaches 100 degrees Celsius. Alright, so first of all, this one here, I am going to identify this as derivative of temperature with respect to T, okay, and it's equal to 0.3 degrees Celsius per second. So you know that 0.300 representing 3 significant digits, and I just want to write 0.3 in calculating this number in relation to whatever calculation that we are going to perform next. Alright, so this one is a related rate problem. So the variables you have here, the temperature is 100 degrees C. So if you have, let's say 90 degrees Celsius, the rate is different, right? So this one change affect the other. And how fast is the resistance changing when we have the temperature reaching these values? So how fast the resistance changing is, we talk about the rate of change of this resistance. It means that they are asking us for derivative of the resistance in terms of time. Okay, so we identify our variables and the rates, and then what we do is we are going to differentiate both sides of this equation, and we will differentiate it implicitly. Alright, so I will write derivative of R with respect to T and derivative of 8 with respect to T plus derivative of 0.02 T squared with respect to T. Okay, differentiate implicitly, you need to write derivative of the variable, each of the term with respect to time. Okay, so now you see, this now identify that this is the unknown that you have to look for, which we already have it here. Okay, so I want to note here the unit. The key is the unit. Okay, so I put here the key is a unit. The unit indicate to me that is the differentiate the temperature with respect to time. So therefore I have degree C with respect to time over like degree C per second here. And can go ahead and differentiate the right hand side of this equation. So derivative of 8 is equal to 0. Derivative of constant equal to 0. But to remind everyone, I'm going to put dt over dt because I know that that and that cancel out. And now it's preparing us for the next step. Okay, derivative of 0.002 times t squared, it means that it will become 0.002 times 2 times t, right? T to the exponent 1, but I must multiply this by the derivative of temperature with respect to time. So this is when this rate comes into your equation when you calculated it. So this rate right here, you don't want to miss that. It will go in here when you calculated it. Okay, so all we have to do is to substitute the values that are given to us into this differential equation, and we solve for the unknown. So 0.02, I time this with 2, I times with 100, and I time it with 0.3 degrees Celsius per second, and my final answer should be 0.120. I will put a 0 there because I want to present it as 3 significant digits. So they said that the resistance measured in ohm, and they asked for how fast, so I have to present it as per second. Alright, so we are going to make note here is 3 significant digits. Okay, working with this type of problem, we have to be mindful our decimal point, how many decimal points that how many decimal places that we are going to keep in our calculation. So at the end, we want our number to be as precise as possible in terms of significant digit. And how do we determine the significant digits that we have to round to for our final answer? Is you take a look at our word problems. If our numbers given to us are given in 3 significant digits, then we have to present our answer in 3 significant digits. I want everyone to note here that the temperature as 100, this line above here, indicates that I am given 100 as 3 significant digits because of the line above to indicate that the 0 is significant. Alright, so I hope this and this example clarifies the step that we need to use. And the key here, the trick I want to show to everyone is take a look at this unit that given to us, degree C cell per second, then it should representing a rate. Okay, and in this case, the rate is in terms of differentiation or in terms of derivative, so it's the derivative of temperature with respect to time. All right. Okay, so let's move on to the next example. So we are talking about 2 resistors connected in parallel. Okay, so everyone is familiar with this formulas for sure. If you have 2 resistors connected in parallel, then to find the total resistance is the product over the sum of this here. So this formula works only when we have 2 resistors connected in parallel. If we have 3, then we cannot apply this. Okay, if we have 2 resistors, then we have the product over the sum. At an instant, R2 is 145 ohms, and R1 is decreasing at the rate of this. So now we are going to read this sentence very carefully. So R1 is decreasing at the rate of 19.5 ohms per second. So this ohm per second will tell me that I will have the differentiation of the resistor with respect to time. Alright, so I am going to write this down. So derivative of R, but what R is this? Is R1, right? with respect to time. So dr1 divided by dt will give me 19.5 ohm per second. But I am going to remind everyone that we are going to attach the negative. It's because we are talking about decreasing in this case. Okay, so because of the decreasing, we are going to attach the negative. And the unit here reveals to me that I can find the differential factors right here. So dr1 as a function of time, and then with respect to time, if I differentiate that, it will be equal to negative 19.5 ohms per second. So in that case, okay, so R2 is fixed, right? So I have R2 at an instant when R2 equal to this value, R1 is decreasing. Find the rate at which R is changing when R1 equal to 195 ohms. So what I'm going to ask you to do is follow the sentence, and what we do is we go like this, okay? At R2 equal to 145 ohms, then I will have dr1 over dt equal to negative 19.5 ohm per second. Okay, I have to find the rate at which R is changing. So that means I am going to looking for derivative of R with respect to t, the rate of change of the total resistance when my R1 equal to 195 ohms. Alright, so we have this four variables and four rates, variable and rates, I should say that. So we will find the rate of this R1 and the rate of this total resistance, and R2 and R1. So four rates and variables in order for us to solve for this related rate problems. Okay, so it's more like we translate exactly what is written to us here into mathematics, right? At an instant, R2 equal to 145 ohms and R1 is decreasing at this rate. So I know that I identify this as the rate because of the unit. Find the rate at which R is changing, so total resistance will change. Then I know that the rate of change of the resistance will be dr over dt when R1 equal to 195 ohms. Okay, so let's put all of this into the equations. Okay, so R1 times R2 plus R1 plus R2. So what I am going to do is asking you to make sure to know that the variable that we are going to use is the R2 in this case, but the R1 we'll just leave it as the variable R1. Okay, so the R2, the values for that is 145. So we substitute into this equation, but R1 will stay as a variable. Okay, so I will have R equal to R1 times R2 divided by R1 plus R2. Alright, okay, so R2 is 145, affecting the change in this variable R1. So R2 equal to 145, affecting this variable R1. So that means I am going to put 145 times my R1 divided by R1 plus 145. Okay, so don't forget that at the values of R2 equal to 145, I am having this R1 affected by it. So in the way that like I mentioned earlier to everyone, this value is fixed. So that means you are going to substitute it into the equation right away. And R1 is changing. Okay, so I can say that find the rate at which R is changing when R1 equal to 195. But I can say this too. Find the rate at which R is changing when R1 is equal to 200, right? So don't forget that it's kind of tricky to figure out which values is fixed and which values is actually changing in this case. So in this case, R2 is fixed because we measure it when we actually put in 145 ohms for this R2. Alright, okay, so now we are going to differentiate. That means I'm going to find dr over dt equal to what? Alright, so this poses a little bit of challenge because I am going to ask everyone to use the quotient rule. Okay, so how do we work with quotient rule? Quotient rule is, I'm going to write the result for you here. V du over dx subtract u dv over dx, everything divided by v squared. So that means you are going to identify u and v, and u is always the numerator, v is the denominator. But we need to differentiate all of this in terms of time, right? So we differentiate implicitly. At the same time, we have to apply the quotient rule. Okay, so I'm going to identify u equal to 145 R1. Okay, and then that means my du over dt is equal to d of 145 R1 as a function with respect to t. Okay, so du over dt. So in this case, I should have 145. Okay, derivative of 145 R1 is 145, and I multiply by derivative of R1 as with respect to time. Okay, so everyone keep this in mind because this is our differentiating, but we have to do it implicitly and we differentiate in terms of time. So what I should do in this case is I should change this into t. Okay, so now I will change it into t because our variable we have to differentiate with respect to time. And the quotient rule, we always remember that v du over dx subtract u dv over dx divided by v squared. But our u and v is we have to differentiate in terms of time. So I now switch it into in terms of time here. Okay, so what is v? Okay, so v is equal to the denominator, so R1 plus 145. So now I will have my dv as a function of time could be equal to the d of R1 plus 145 as a function of time as well. Okay, so then what you do is you are breaking this into two, right? So derivative of R1 as a function of time and derivative of 145 as a function of time. And you see this is actually equal to 0 because you are differentiating a constant that is turned into a 0. So basically my derivative of v as a function of time is just dr1 over dt. Alright, so I should put in a number here. There should be a 1, right? Derivative of r1 is just 1, but we have to multiply by derivative of r1 as a function of time. So what is v squared? So v squared is just r1 plus 145, all of it squared. Alright, okay, so let's substitute into our equation. So now I have dr over dt. So first of all, v is r1 plus 145. and then I multiply by du over dt. So I multiply by 145 of dr1 over dt. Subtract that with 145 times r1 times dr1 over dt, and the whole thing is divided by r1 plus 145 all of it square. So now let's double check. So this is our v, okay? This whole thing here is our du over dt, okay? So this is du over dt. We are good with that. And the next one is u. So this one is u's here. And this one is dv over dt. And this one is v squared. So we are good. Now I'm going to substitute the values given to me into this differential equation. So now this is when you are going to substitute R1 equal to 195 ohms. Okay, so I will have 195 plus 145 multiplied by 145 and multiplied by negative 19.5 and subtract 145 times 195 and multiplied by negative 19.5. The whole thing divided by 195, add with 145 all of it square. So don't forget, these are all bad maths now. Okay, I'm going to give you the number that I got. Okay, this whole thing will be divided by this number. Okay, so in the end, my dr over dt will be equal to negative 3.55 ohms per second as decreasing. So let me rewrite the second here. So this one is the decreasing. All right. Okay. So I have a couple minutes left. I will work with example 3 and example 4 in the next video. And let me recap what we have here. All right. Okay. So what I have here is I have two resistors connected in parallels. And in solving for the R, the total resistance change when R1 equal to 195. So reading this sentence, you realize that this R1 is changing and then it affects the other variables in here. So that means the R2 is fixed. Okay, so this unit will identify the differential of R1 as a function of time. And because of decreasing, we have to apply the negative values. Then after you identify the fixed value for R, you substitute into this equation. And you know that R1 is changing. Okay, so that's why you leave the variable R1 and then you differentiate accordingly in terms of time using the quotient rule. And differentiate in terms of time, we have to make sure that we have to multiply by the differential factor of the derivative of R1 over dt in this case. Substitute into the equations. Make sure that we have the formulas and all our number correct. And bad maths, okay? And here's a number that I got, and in the end, the final answer is negative 3.55, representing decreasing as indicated in the word problems here. All right, I think I will stop here because I actually used up almost 30 minutes. I have a few seconds left. All right, thank you, everyone.